Welcome to my Commodore 64 Games memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Turrican, published in 1990 by Softgold, developed by Rainbow Arts and programmed by Manfred Trenz. Musicians were Ramiro Vaca, I hope I got your name right, Chris Husselbeck and Stefan Hardwig. This game was actually one of the first ones that I saw on the Commodore 64 that did multi-speed 8-way full colour scrolling with almost the full screen. We're going to be looking at the disc version today. When the disc version loads, I can see actually there's a little tra-la-la message just at the end of the first screen bank, just down at the bottom. We can see it's using the vector there at 0326 in hex, and that little tra-la-la text message kind of like jumped out at me way back in the day when I was looking at this loader. The loader for the disc version for this part here, which does the sample introduction, is actually very fast. I was actually very surprised at how quickly this actually loaded stuff. And then we get into this rather lovely loading screen with, I think, some sprites in the upper and lower borders there. Mostly visible in the lower border, of course. Now this loader, the disk loader, actually seems to decompress going backwards through memory. You can see there it's doing a mixture of reads and writes in the memory view there with ICU. So decompression while loading is quite an interesting way of doing it. That's probably why it's so quick, actually. I mean, the screen is on still, so it's not as quick as the sample load at the very beginning. So when I saw this title screen with the lovely colour bars, now I've extended the border for the ICU debugger view, so that's why you can see the break in the colour bars there. So looking at here, we can see at 9400 in hex, we can see this message from the programmer. Hi folks, the maniac is back. One question, why do you want to crack this proggy? Can you imagine how much work I did to make this game? To make a game like this, etc, etc. Please don't crack it, please don't spread it, basically. Working 14 hours a day. Blah blah blah. So it's not uncommon to see messages like that in games, as we can see from the other videos that I've done. Here we can see an EOR and then a shift with the CIA 2. So the disk serial connection. This, I'm just having a quick little look here with the disk loader just to see what it does. We can see the corresponding code on the disk here, where it's using a faster lookup by the looks of it, and then storing the values out to its serial output chip, which sends data back to the Commodore 64 basically. So quite an optimal fast load really for this part of the game. We can see the structure it uses as it's loading through memory. So we'll skip past that. So yeah, the backwards loading while decompressing is really quite special. quite an early example, really, I think, of decompression while loading on the disk version anyway. Then, of course, in the disk version we have this turn the disk message, so I'm going to insert the other disk image now. This is after the title screen, of course, and we can see that it's still employing that backwards loading and decompress while loading routine. Interestingly, when it's going through loading the memory, loading the level memory, it's still got this message at 9400 in hex sitting in memory. What I do like about this level load routine is that just the very simple, very stable raster bar while it is loading the information from the disk. It's something like that. It's a nice little touch which just tells me that the programmer was polishing this game to make it nice and neat and present it really well. I mean, the title screen also presents it really well too, but here we can actually see somewhat that the disk, that the drive code sitting inside the disk's memory that we can see here, and the corresponding C64 receive code is actually a lot different to the fast loaders that were used in the earlier part of the game. But it's still employing this backwards decompress while loading. And now we can see that the please don't hack me and spread me message from the programmer has now been overridden. So we can see here that we have two screen blanks starting at C800 and obviously CC00. That means that the first couple of K in the memory for the third last bit bank, the third one, fourth one, at C000 is the character set, and we only have one character set visible for the game. We can see that the two screens there at C800 and CC00 in the debugger graphics map text screen view there contains a double buffered screen. So I want to see first of all the code which does the color scroll for the Commodore 64. Don't forget that the Commodore 64 only has one color screen in this particular text-based mode, and that color screen is always at D800 for the whole kilobyte, in other words 4 256 byte long pages effectively, roughly. Yeah, I forgot to set it back to the computer when I was trying to find the breakpoint. There we go. So this is the code for scrolling the color map. Now it's worth reminding ourselves, I think, how a computer screen is actually drawn. Now the Commodore 64 of course uses, in the old days it used CRT, cathode ray tube, basically televisions, or a monitor, but basically the same kind of thing. Now the Commodore 64 outputs a video signal, and the TV or the monitor will synchronize to that signal from the Commodore 64 and then scan its screen in synchronization with the Commodore 64 to output the picture. Now, a picture on the TV is oriented like this. So I'm just drawing a quick mock-up of the Commodore 64's border here, and then like a dark blue screen color. It's not quite the right color, is it? Yeah, well, there we go. We'll choose a little bit darker one. Okay. And then in the middle of the screen, of course, we have some text. What color should we use for the text? Wow, I've got a big font there. Let's change that to be smaller. Okay, so this is the screen. This is a Commodore 64 screen. So the Commodore 64 outputs a video signal, and the TV or monitor, same kind of thing, will synchronize with that signal and then start outputting colored pixels on the screen by scanning from left to right and then advancing down one pixel line and then drawing pixels left to right again. And the TV does this basically for every horizontal row of pixels that's visible. And the Commodore 64, a PAL Commodore 64, will do this 50 times a second, roughly. It's, you know, plus or minus a little bit, but it's basically 50 frames per second in PAL and 60 frames per second in NTSC. So the TV renders those pixels, and basically the scan goes down from top to bottom, left to right, top to bottom, all the way down the screen. So if we want to scroll the screen information on the text screen, we need to copy from the bottom going up to the top, and we need to copy from the row above to the row below, the row above to the row below, row above to the row below, and we do that, you know, roughly 20 or 25 times. The thing is that while the TV is scanning down, we are copying backwards up through memory. So this means that the scan from the TV coming down is in opposition to the memory being copied going up the screen. Now this is an issue when it comes to the color RAM, because the Commodore 64 only has one copy of the color RAM. So if we try and update the color memory at the same time that the TV is wanting to scan that color memory and generate the image, then we're going to be getting some weird flickering effects. So we want to try and time this color scroll so that it does not interfere with the scan of the TV. And that's what that great big long piece of code there does. It starts at line 218, and by the time it exits the routine at 18 EC. Actually 18E9 jumps back to the top of the scroll. So this loop is partially unrolled. It's wanting to do a copy for every single row of the color memory that it wants to copy, but it's using an indexed register, the X register, to copy from right to left, but it's doing the copy from bottom to top, and it's copying alternate lines, but it's going up the screen because the screen scrolls up. This is the most difficult color scroll to try and synchronize on the Commodore 64, because as we looked at just now, the copying in the memory is in opposition to the way that the TV wants to scan, or the Commodore 64 wants to scan down as it's drawing the picture. So to time this needs, it takes quite a lot of work for the Commodore 64 to copy all of the color information row by row. We can actually visualize how much time it takes for the Commodore 64 for its CPU to do the copy. And we can look at that in Turrican itself. So 1866 is the start, where it sets up the index register with 27 in hex. 27 in hex is of course 39. And it then finishes at 18 EC. Basically, the register, the X register for the memory index copy there is FF, because that's the ending value for the loop, and then it just does an increment X, and then it stores it in 206. It stores it like a flag or something like that. So we can see that the raster position is line 37 from the register view there when the color scroll finishes. So the position for the color scroll, the code time for the color scroll, actually begins just where that horizontal screen split is for the score panel. And it goes all the way down through the border area and then comes all the way up to almost the top of the border for the next screen. Because don't forget, when the raster time goes off the bottom of the screen, then we start drawing the next screen, or rather the Commodore 64 VIC chip starts drawing the next screen. We can see that the interrupts are enabled, so this is what we call mainline code. This is code which is not running as part of an interrupt. But we can see here that it's using an indirected jump method at 71C and 71D, which contains the address for the routine to actually execute. So it looks like, I don't know, it looks like it might be using some kind of like state machine or something like that, perhaps internally, where it's calling different routines at different times. And this routine happens to be one of the most important routines, which is the color scroll routine. So to show on screen exactly how much time this color scroll routine takes, I think what we can do is that we can use an increment border effect, and we'll just change the instruction at 1868. So instead of loading with the color RAM, we'll just do an increment with D020. Now what this does is that it will increment the border once for every vertical column on the screen, so for all of the 40 characters across, because that's how this loop is set up. It does mean that we'll see this white line here where it doesn't actually read the memory correctly, but as I jump up and as the scroll down routine for the color memory comes on, then we can see the border timing. And the border timing tells us quite conclusively here that the color scroll is timed to start exactly where that screen score panel split occurs, and we can see that this color scroll routine finishes a few rows just above that border. And this is no accident, because the color scroll routine needs to finish at just the right time to allow the sprites up at the top of the screen to be updated. We can see that the last color scroll update is at 18E0, and that was reading block colors, I'm guessing, and then storing it into the color RAM. And that updates the very top of the screen with new color information. We can see here that each individual line that's being drawn on the screen here with that debug color here represents one screen column worth of copying, and then there we can see that it exits, or it will exit just about here. Something is setting the border color back to black after a certain amount of time, but that's fine, so there's just some extra border color set going on somewhere in the code. Maybe we'll look for that later on. But we can see here that there it is. There's all of the color scroll. All of the time taken just for the color scroll. So we can see that actually the color scroll, using a semi-unrolled loop, okay, using an index, but still it's relatively semi-unrolled, partially unrolled. Unrolled meaning that there's a repeated block of code which does the very similar thing but with different offsets, for example. That means that the loop is partially unrolled. We can see how much raster time, how much CPU time it basically takes, and it takes a good chunk of the screen time. Now the rest of the screen time will be for example, rendering the sprites, animating sprites, playing sound effects, updating the bullet positions, and so on and so forth. So considering that this game is not using a cartridge, and considering that this game just basically has the code loaded for the level, it's actually doing relatively quite a lot, and it was really very impressive at the time. So yeah, this is where that last color block update is done. Now, of course, when you're scrolling the screen down, you need to introduce the next row of color information up at the top of the screen. And that comes from the map as it's scrolling into view. And that can be calculated elsewhere at different times. It doesn't matter because it's stored somewhere temporarily in memory, like at BFC 0, for example. So after this color scroll is done, I expect it will update the sprites, because I don't see any large amount of time being taken to update the sprites elsewhere, because there's no large gaps in these raster lines here for the color scroll update timing. So I expect that the sprites will just be updated just about there, which is an intriguing point in time to actually try and update the sprites, because if you want the sprites to smoothly come in from the top of the screen, then it doesn't really give enough time for the full sprite to actually start being updated. But okay. But that's only when it's updating the color scroll. Now the color scroll is only updated when the screen wants to move the whole character step, of course. When the hardware fine pixel vertical and horizontal scrolling is being updated for all of the other pixel positions of the character, then the color scroll is not really needed, because the hardware scrolling scrolls between 0 and 7 pixels horizontally and vertically. So here we can see that just immediately after, practically, the color scroll has finished, then the first sprite updates are being done there. We can see a store into the sprite register D006, for example, at A4C, and we can see that it's updating the sprite MSB X register as well, as you would normally expect. It looks like it's loading coordinates, and then it is storing them into the relevant sprite registers. So this is just the very beginning of the sprite update for the current screen as it's being rendered. I think this accounts for the occasional sprite glitches that I do see when scrolling the screen down when jumping up, for example. We can see quite an impressive number of sprites there as well, with the screen scrolling. Obviously some multiplexing going on there. If we have a look at the sprite layout there, actually we can see that there's quite a lot of unused memory for sprite frames. At the end of memory there, we can see that there's a good like almost three rows of unused sprite data. The effect of the teleporter coming in was basically the updated sprite. It was animating a sprite there. If we have a look at the last but one sprite, look, that's interesting. The continue game over sprites actually were replacing the little both the explosions and also the little player controlled kind of like wheel of death, if you like. So again, the backwards loading while decompressing routine, and here the title screen comes back again. We can see where the sprites were copied from. Excellent piece of music here, by the way. I like this one for the high score. In fact, I don't get a high score. I'm quite rubbish, obviously. We can see it's just a text screen for this, with obviously sprites over the top of it, little animated sprites. Ah, there's the title screen. So actually the title screen had a little bit of loading going on, I think. Maybe. So it loaded some data, and then it asks for the disk side to be flipped over again. Obviously, I do wish that this game had at least level 1 on the same side of the disk as the title screen. To be honest, we can see all of the sprite frames got practically refreshed, and there we go. We can see actually that the code for the scrolling doesn't get reloaded when it goes from the title screen back to the level, so we know that that code just sits in memory. Interesting. So when things get really busy, it's interesting to note that the sound effects start slowing down. So I think the sound effect code is running in the main line, basically, or maybe it just doesn't do the update. Maybe it realizes that time is running low and it just doesn't do an update at all. That could be the case. These are diagonal scrolling down routines, so they're not going to have the color bars. I only added the border color update to the straight down scroll. So that was looking at the color memory scroll, the color screen memory scroll. Now let's have a look at the text screen memory scroll routine, because we have two text screens side by side, basically. Two different screens. We have what's known as, of course, double buffering. So let's see if we can have the memory point show this code. Now, the screen data, the text screen scrolling code, looks a little bit different to the color scroll. First thing you might notice is that it's not doing the entire screen scroll all in one go. It is doing this chunk of screen rows here, so it's doing 1, 2, 3, 4, 5, 5 screen rows first, and then exiting, and then it looks like it's doing the remainder of the screen rows as a scroll here. And we have two copies of this routine, semi-unrolled, like the color scroll, but in two different chunks. And that's because we need to copy from one screen to the other, or from the other screen to the other screen. So we need to have copies going both ways, because we're using a double buffered text screen here. So if we want to see the timing for the text screen scrolling, we can use a very similar technique to the color screen timing display. So we can update the border for these text screen scrolls. So we'll put an increment D020 there at 17C2. And we'll put another increment D020 at 1825. And we can see the time taken for each of them. There we go. And we can see the timing for the text screen scroll is actually during the rendering period for when the screen is being displayed. But because it is using a double buffered scroll, it's copying from what is currently visible to what is currently not visible. And then the screen is being flipped over, so that this copy is basically invisible to what is being viewed on the screen. I'm just trying to catch the screen now when it is scrolling down, and then I can use the frame by frame advance so you can actually see more easily on the screen the actual timing that the character screen scroll uses. Let's jump up, there we go. So that's the other routine, that's the shorter 5 character rows scroll time there. And then the previous, then oops, flip past it a little bit, let's do that again. No, missed it. But anyway, the previous one was showing the screen timing for the rest of the character rows. So it seemed to do a large chunk of the off-screen scrolling, and then it did a color scroll, which takes up a large amount of time, and then it seems to do, if the scrolling needed to be quite quick, it seemed to then do the scrolling for the last 5 character rows. So effectively scrolling the full text screen and then scrolling the full color screen basically gives a maximum Y pixel movement of 4 pixels per frame, and then of course because each character is 8 pixels tall or 8 pixels wide, then that means there needed to be a full color update every other frame. We can see there that actually in the IRQ exit code there, which seems to be common code, that's where it was doing a store with black for the border color at 8DA, into storing it into D020 in hex there, which is the border color. So that's why we were seeing the border color get returned back to black. There are other ways of doing a full screen or almost full screen full color scroll, and you can, for example, interleave the scroll update, and if you don't use indexed addressing, if you unroll the loop fully, basically by having load and store absolute addresses instead of load and store absolute with indirect indexed value with X or Y, then you can make it quicker. And if you really want, you can try and chase the raster beam as it goes down the screen. And as long as you have your color information off screen, or as long as you split the color scroll up into chunks, you can try and chase the raster position or raster beam as it travels down the screen. You can do it that way too. That gives you a faster scroll, but it gives you less time for all of the rest of your game update logic. But it's certainly possible to do that. It really depends on how much memory you want to dedicate to code to do the scrolling compared to how much time you want your code to take when it's executing. Generally speaking, the more you unroll your code, the larger your code, the less time your code is going to take when it executes, because when you unroll, you don't need to have so much indexed addressing. Indexed addressing takes longer to execute than non-indexed addressing, of course, because the CPU doesn't need to do any more additions or anything else like that to the memory address. I'm just having a little look here at the interrupt routine, and we can see here actually it's clearing the interrupt flag during an interrupt, which means technically speaking, if another interrupt needs to happen, then this interrupt code will get interrupted with other interrupt code. Okay. But I think maybe the interrupt is coming along and up the initial sprite update up at the beginning or up at the top of the screen, which is quite intriguing. Maybe it's not doing it in the main line then. Huh, okay. It's just an interruptible interrupt. Quite a risky way of doing it. You have to maintain your code quite well. You have to put things onto the stack usually, or make sure that your register storage for each interrupt doesn't overwrite the previous return. And that's probably why we see a PLA TOA TAY, PLA, TAX, PLA, and RTI, because it's storing all three registers and pulling them off the stack and then restoring the interrupt. Or RTIing from the interrupt, sorry, returning from the interrupt. It's interesting to note that this indirect jump is using the default kernel extended 0 page vector 314 and 315, right? I guess, you don't have to use that memory address. You could use any memory address at all, but it just seems to be using that one. It is not using the kernel, I don't think, interrupt handler though. It seems to be using the kernel vectors directly. It's not using the extended 0 page IRQ handler. It's just reusing that memory address just because. Looks like that was executing or returning from the sound effects routine actually. So if we change the interrupt handler so that it increments the border, we can see where the interrupts are occurring on the screen. We can see that there's definitely interrupt there for the screen score panel split. There's an interrupt kind of like happening down near the bottom. It doesn't seem to be doing much. And then there's probably an interrupt or two for the multiplexer going on there as well. Look, we can see interrupts moving up and down the screen as there are more sprites occurring. Let's move the mouse out of the way. I thought there was a power-up block at that position. Oh well, never mind. The weapons effects are mostly characters, in fact almost always characters, I think. But they do look rather special, don't they? They blend in very well with the background. We can see more interrupts happen when there are more multiplexed sprites going on the screen. Let's turn off the interrupt color updates. Lovely scrolling, isn't it? And lovely sprite updates as well, and stuff like that too. Considering how much the game is throwing around, the C64 tends to handle it quite well, really, kind of. See if there's anything else worthy of note. We can see the disk code is alternating between roughly 500 in hex and then going into the disk's ROM there, and so the disk ROM routines are being used for at least some block loading and probably decoding, but then the majority of the fast load uses custom drive code. We can see that in synchronization with the C64 side. We can see that the top of the logo is unsurprisingly a bitmap, and it's got sprites over the top, and then the rest of it is a text screen mode with color bars and color ramp updates for the text. Again, unsurprising. Interesting to note that there are no sprites over the color bars, and that's usually because it's a little bit more difficult to time color bar updates with a whole bunch of sprites over the top of it. It's not impossible, it's just a slightly more difficult thing to do, and if you don't have to, then it's usually easier not to. Let's insert rather the other side of the disk. There we go. Disk code and drive code and C64 code as expected. Teleporting in, quite a nice little effect actually. So it's interesting to note that the second sprite, 0, 1 and 2, so sprite number 2, so the third sprite basically, is expanded in the Y direction, so it's using the Y expansion flag there. We can see a yes and a star next to it. Excuse me. And so Turrican, the main player sprite, is actually updated near the top of the screen there, look. So the Turrican sprite comes into position there, and then we can see that it's comprised of 3 sprites. A multicolour sprite at the top, a multicolour sprite for the legs down the bottom, and then a third sprite which is expanded in the Y but behind the other 2, which gives the main white colour for the body of Turrican, but the other parts of the multicolour sprites are transparent, which you can see here, which lets the white colour through from the sprite number 2 in the background. So actually Turrican uses 3 sprites for the main player character. Quite a common way of enhancing the number of colours. Other games used to do this kind of thing too. Sometimes they would use a black screen, a black sprite overlay, and this is an underlay, a white sprite underlay. We can see here the pixel timing for the screen split does the usual kind of stuff of updating all of the screen vertical scroll registers and setting up an illegal text screen mode, and then doing the split, and then coming back and then enabling the text screen for the score panel down at the bottom. The usual kind of stabilization logic there. So there's the entry for the interrupt. You see it's acknowledging the raster interrupt and then pushing the accumulator X and then Y registers. The code that was being interrupted by the interrupt is shown there, but then we get into the main jump for the interrupt, and so this is loading with D251, but basically it's loading D011. The VIC chip registers are mirrored, going up all the way up through memory in this memory range here. So D251 is just basically loading with D011, which is the screen Y scroll, right? It's then using the screen Y scroll pixel position to update into this table, which delays a certain amount of time depending on what the Y hardware pixel scroll value is. The reason why it delays by looking up into a table is that it wants to do different delays depending on the Y pixel scroll value, and that's because the bad line will occur at different times. So it wants to compensate for the bad line occurring at different scroll values, and so it's having to do this delay loop, and it does the delay loop with an X count here, and it delays it until such a time that it knows that it can safely reset the screen vertical scroll. And it also sets up here an illegal mode. So it's going from multicolor text to illegal text, which disables the screen output circuitry on the VIC. So it starts outputting black data effectively. And then once it knows that it has safely stabilized the Y scroll and it has safely turned off the screen, then it does some optimized stores here for resetting the sprite X positions. So as we keep moving through the code, we can see all of the sprites start accumulating themselves on the left hand portion of the screen. And it does that to basically put all of the sprites out of view as quickly as possible. Because at this screen split here, position here, you don't want the sprites to be visible over the screen split. So we've gone back a little bit through the interrupt routine. We're just going through the delay loop, and there we go. I'm just showing you again exactly what happens with the screen display as it's basically updating those registers. D291 is the same as D011. Just to emphasize the point here, we've got display mode multicolor text there, and then if I move to the right to the cycles to the next few cycles, so rewinding back through the interrupt, we run the interrupt. Okay, we run the interrupt code. This is a good thing about C64 Debug GUI, is that you can run backwards and forwards through the code, and you can see exactly what the code is doing at each particular cycle and how it synchronizes with the screen. So again, load accumulator with D251 is the same as D011, which is the screen Y scroll register in the VIC chip. It extracts the lower bits, which is the pixel scroll value from 0 to 7, the hardware Y pixel scroll. It transfers the accumulator to Y, and then it does a load X indexed with Y to do the delay load. Runs that little delay loop. The couple of no ops at the end are basically some finer adjustment timings for this delay loop, and then it switches to the illegal screen mode here, and then forces all of the sprites to be visible in the border on the left hand side. Interestingly, it updates the sprite MSV register at D010, so at C012 there. It updates that in the middle of the sprites. So it updates the first, 1, 2, 3, 4, 5 sprites. It then updates the MSBX register to make everything go on the left, and then it updates the last 1, 2, 3 sprites there. Bing, bing, bing. You can see now all of the sprites are accumulated on the left hand side underneath the border, so they're not visible anymore. So hopefully this screen split is quite stable and quite accurate in terms of sprites. And we can see here that just at this cycle position on the screen, which is just synchronous with the left hand border here, it has finished updating all of the sprite registers. Just about. So that hopefully we don't get any sprites visible on the screen. It's also set the screen color at D021, not the border color at D020, of course. It's then going through and then setting up the next interrupt. The next interrupt comes along eventually. The next interrupt will come along just in time to turn on the score panel display. So there's the delay for turning on the score panel. Again, the score panel turn on routine also has that delay to cause the code to run at precisely the right point in the raster line schedule, because the interrupt starts at the beginning of the raster line. So you want your code to be precisely timed, you have to delay it a little bit. And then, there we go, storing it in D1, which is effectively D011 again, which turns on the screen display circuitry within the VIC by turning it back to a multicolor text mode as opposed to the illegal text mode, which displays black. It's still outputting some pixels, in that illegal text mode, but all of the pixels for the characters are black, luckily. So we can see that there's a little bit of multiplexing going on there. I mean, the sprite which is coming along on the bottom of the screen actually is inside the score panel. Now, the score panel screen is going to be set up so that the sprite definitions are all pointing to empty sprites. So we don't see that little bird fly over the score panel, but still it seems that there is a sprite being displayed there. Now, actually, normally I would have not had that sprite being even considered for multiplexing because it's over the score panel, but hey ho. Not everyone does those kind of optimizations, but we can see here now that there are certainly some multiplex sprites being updated now, and we have more than 8 sprites on the screen. And we can see that the sprites get updated with the normal kind of like earliest possible multiplex update. So after each sprite has finished displaying, those sprite definitions are then reused for sprites further down the screen. So we can see that happening there. But we can see those updates being done in the first couple of character rows for the screen, which is an intriguing way of doing it. It means that actually the sprites up at the top of the screen, depending on what's happening, could be flickering a little bit. But we can see this game uses a lovely combination of high-res characters. The green plant stuff on the right-hand side there of Turrican is using high-res characters. And then it's also using obviously multicolored characters for other parts of the map as well. So this is what really taught me, if it wasn't obvious already, that it was definitely doing a full color scroll. If it wasn't doing a full color scroll, and if the whole screen had to use the same color, then it would not be possible to mix the multicolor graphics with the high-res graphics in this fashion. Interestingly, we can see that there's a sprite on the right hand side trying to come on, but it's not quite coming on, so I'm guessing that that's an enemy. Again, I would not have had this even being considered for multiplex sprites updates. I would spend a little bit of extra time on the code to effectively reject or clip out these sprites and remove them from the animation completely. Sprites that are off screen that you can't see because they're completely hidden by the borders, really shouldn't be added to the multiplexer, because you're taking away potential sprite updates for sprites which could potentially be visible on the screen, you see. So you want to try and maximize your rendered stuff on the screen as opposed to rendering them off screen in the border where they're not going to be visible, or over the score panel especially where they're not going to be visible, right? Yes, it takes a little bit of extra CPU time to accurately reject or clip sprites off the screen, but you get a much richer, much busier view of visible data on the screen, so it makes it look like you're updating more for the game. Well, because you are. Anyway, so I'm just moving around now, and I've noticed that the C64 debug GUI with the current, I guess it's the current keyboard bindings, it doesn't play very well with Turrican's keyboard handler. Turrican seems to want to be doing the pause update quite often when I'm trying to move around, especially with the cursor keys. Especially when going to the left. That's annoying. I think this is a combination of keys getting stuck and also the keyboard handler routine in Turrican is getting confused with what should really be isolated as keyboard input rather than joystick inputs, or hitting the run stop key, which I'm not doing. I'm using the cursor keys. One little interesting thing to note is that since Turrican seems to be going into the pause routine when I'm moving the keyboard joystick, then it seems that rapidly going into the pause routine causes enemy sprite spawning updates to not occur, and the enemies seem to pause, whereas Turrican seems to move around still. Look at that. So, it seems that the pause routine is, if you rapidly, I guess, pause and unpause by holding down fire, then you can seem to move around the map quite a lot without any enemy updates going along, happening. See, look, and there we go, everything spawned. Okay, so how many sprites do we have there? Like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, The continue, yes, no sprites are horizontally expanded. And we've definitely got multiplexing going on there with the sprites because we can see them. We see the sprite borders there. Yeah, interesting, but okay. So yeah, anyway, that's Turrican. I just really wanted to have a look at its screen scrolling and how the screen color RAM scrolling was timed, and also a quick little look into its disk loader as it decompresses, and also the sprite multiplexer updates. So yeah, Turrican, very technically accomplished game. Very interesting to try and reverse engineer, especially when I was young and trying to do something very, very similar for Tusari 2, which never really got done way back in the day. It's one of those projects that I wanted to try and complete but ran out of time to. So yes, thank you very much for watching these crazy retro gaming Commodore 64 videos. If you like this kind of stuff, then please do consider liking or subscribing to my channel, and there are buttons for that purpose down below, and that would be great, wicked, fantastic, wonderful. Thank you. Take care, have a great day, wherever you are.